Is it bouncing? Did I turn my mic on? La, la. All right. I will begin with a word of prayer. And try to get the, anyway, let's begin. Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. All right, let me return to this one more time. So I really think that the reason for this actually providing the decomposition, it's relatively simple. So I guess there's two steps. The one step is that this is clearly equal to f of z when we're inside the annulus, right? So if you think about this, right, if z is up here, right, if z is there, that means that z is within d plus. I should just say d plus. I don't. Oh, okay, boundary. Excuse me. So if z is up here, that means that we're assuming f is holomorphic on the simply connected region. Therefore, by Cauchy's integral formula, if z is in here, this is f of z, right? And if z is in d plus, then z is not in d minus, hence we're integrating a holomorphic function over a simply connected region, and actually going back to Cauchy's theorem, not even the integral formula, but the first result we found that if the function is holomorphic over a simply connected region, that it integrates to 0 on the boundary, we know that that's 0. All right? So you've got f of z, you got 0. In total, it equals to f of z, right? What's the other case for z inside the annulus? It could be down here, right? It could be down there. So in that case, if z is in d minus, then z is not an element of d plus, so this is 0. On the other hand, that is what? F of z. So we either have f of z plus 0 or we have 0 plus f of z. In either case, f of z. And that's for any z in the r less than modulus of z minus z naught less than s annulus, right? Okay, so step number one, this reproduces the given function which is holomorphic on the annulus at each point inside the subannulus, for sure, right? Then, yeah, well there is of course the larger at the moment, but soon to be pictured. This is a subannulus sitting inside the larger green annulus, which we're actually given that f is holomorphic between rho and sigma in the setup, right? So rho is less than r, s is less than sigma, if I recall the letters right. All right, great. Then the other way we could look at this integral, though, right? So that analysis is just for z within the given rs annulus centered at z naught, right? Next step is to think of defining f of z. Well, rather think of g of z rather as being a function defined by these integrals. And so that's the thing, is I can trade those integrals for the circle integrals that I had last time, right? Like, what was it? I called it the circle, let's see, the outside circle of radius. If I'm doing both of them counterclockwise, right? I'm doing both of these counterclockwise, then this would be modulus of W minus Z naught equals to the outer circle. What was that? S. Was the outer circle S or R? S, okay, good. And then minus the inner circle, counterclockwise oriented, modulus of W minus Z naught equal to R. So I'm saying define a function G by these integrals. All right? Then if you look at that, we can think of, and this is the thing I think that escaped me, that was destroying my intuition last time, is the idea that the Laurent expansion extends past the given domain of where F is holomorphic. We're given that F is holomorphic on an annulus, but the Laurent expansion goes past the annulus in both directions, inside and out. Just like a power series for a holomorphic function might extend beyond the center, beyond the domain that you're given, like we talked about in the analytic continuation. So this, I believe, is the F0 of Z, and this over here is the F1 of Z. Now the thing that I got caught up on was thinking that that Z necessarily was a Z for which the original function made sense, but it's not. It's a new Z. It could be a Z within the annulus, but it could be a Z from outside of the annulus. What happens if you, say, take a point? I mean, so the thing is, these formulas make sense for Z anywhere because the integral is over W, right? So if I take Z outside of the black annulus, either inside or outside, that doesn't make the integral any less valid because I'm only looking at F of W, and F of W is always sampled from these circles where F is given to be holomorphic. And more than that, you can see that these integrals, in fact, would be 0. Well, at least one of them would be 0. I mean, sometimes you could see the integral would be 0 because the function would actually be, holomorphic on that region. We have to think through that more carefully, but I think this is F0, this is F1. The larger point, though, is this one. In order to show that this is actually the Laurent decomposition as advertised, we'd like to show that this limits to 0 as Z goes to infinity. How would you show that that limits to 0 as Z goes to infinity? Essentially, the point is that as Z goes to infinity, you can bound. You can look at F of W over W minus Z, right? And you can see that that's going to 0 as Z goes to infinity. I'm being a little bit sloppy here, but you could supply details to make that rigorous. See, because W is always within this finite region, right? So like W and F of W, they're as big as they get over this compact region. In the extreme value theorem, this is a compact set. F is continuous on this compact set, so the modulus of F attains a maximum. And Z is definitely outside of here because it's going to infinity. So basically, you're looking at some stuff that can get to be so big relative to the annulus, and then you're subtracting this Z, which is going to infinity. So this clearly goes to 0, which is what I need, because if this goes to 0, that means I can bound the integrand here, and in the limit as Z goes to infinity, the ML theorem should show that this integral vanishes to 0, which is what I need because I have to have F1 going to 0 as Z goes to infinity. So these are the things I should have said last class, but, whatever. Yep. Yeah, go for it.
Because if we define these intervals like this, then within the sub-annulus, Z is going to agree with F, right?
Right.
But if we're inside the sub-annulus and if we're inside the bigger annulus and we're outside the sub-annulus, then they might not necessarily agree, right? Definitely messy things happen on the boundary.
Ah, okay. Good point.
So
right.
It seems like the last step would be to say, this would be G sub R and S, and then say that these agree for any time that you make the R and S bigger, then they're going to agree within what you already had. So for anything within the annulus, the overall annulus, you can choose R and S Like, is there a way to clean that up in a closed form?
Well, I think that's the thing, is that if we vary R and S, it doesn't change the integrals by the deformation theorem, because of the nature of the given data here. The integrals don't change if we expand out or contract in a little bit if we study it.
Right. The integrals
So
don't change within, like, if the stuff that's...
I can never actually get to rho and sigma. I can just approach them.
Right.
Yeah.
Yeah.
Oh, anyway, I can give you the page in Ramir where this is proved a little bit more carefully. But this is essentially it. I should probably, I need to go on at this point. The larger point from this, though, is from this we get the Laurent series decomposition, right? So, which is that, if f of z is holomorphic on, let's say, what did I say? Rho less than z minus z naught less than sigma, then there exist coefficients a sub k, right, in the complexes for k in the integers such that what? Such that f of z is equal to the sum k equals minus infinity to infinity of a sub k times z minus z naught to the k, right? And that's a simple, we went through that last time, of course. That comes from the fact that the F0 is analytic, right, within the inside of the annulus, and the F1 is analytic from the inside out of the annulus. And so we can look at the power series expansion about infinity for F1. That gives us the reciprocal terms. And we can look at the power series expansion about Z naught for F0. That gives us the positive, the non-negative terms in this Laurent series, but it's there. And so everything we're going to do today is going to be based on using this Laurent series decomposition to analyze the nature of singularities. All right? So, since I have doubtless, well, I guess we're okay. I thought I ate more time up than I did. So I will not get the projector out just yet. Bethany, you maintain your happiness a slight bit longer. Let's see here. Bethany says, my happiness is not based on whether or not you stop writing on the board. You don't have that over me. All right, very good. That's right. We shouldn't be like that. All right, so where are we? So we had the removable singularity, the pole of order n, and the essential singularity, right? Let's look at the three theorems which categorize those singularities, which explain what does that mean for us in terms of how the function behaves. We'll start with Riemann's theorem on removable singularities, and that's this. The theorem says that let z naught be isolated point, well, isolated singularity, of f, all right? I typically write f of z in here. If f of z is bounded near z naught, then f of z has removable singularity. All right. So the proof is by the Laurent series, right? If it's an isolated singularity, what that means to start with is that we can draw a picture like this. Here's your z naught, and there's some kind of disk, right, of radius. I guess my current nomenclature would be sigma, and f is holomorphic, right? F is complex differentiable at any point inside that deleted disk. And more than that, we have what? We're given that f of z, modulus of f of z, is less than m for, modulus of z minus z naught less than sigma, let's say. So let's choose sigma to be the close enough on which it's bounded, all right? If it wasn't already that, you could make the thing smaller so that it would be bounded, because we're given that f is bounded. Of course, and that means that the modulus of f is bounded. But we also have what? We also have f of z is the sum, k equals minus infinity to infinity, of a sub k, z minus z naught to the k, right? And so we can, and the other thing that I've neglected is we had a formula. What was our formula for a sub? I'm going to use an n instead so it matches my notes. All right, guys? Let's change the k to n just for the sake of matching my notes and making it easier for you guys to compare your notes to my notes later if you want. Anyway, so n. Remember we found a formula last time? That the formula for a sub n, and we put modulus around it, is equal to the modulus of what? Was 1 over 2 pi I integral, right? And it could be around any circle in here, I believe, right? Pick your favorite circle up in here. Sigma over 3. Okay, sure, why not? Oh, actually, I better make it a circle of radius r. So modulus of z minus z naught equals to r. And what was the rule? It was f of w. Oh, I probably should. I finally did z. F of z dz over z minus z naught to the what power? I heard n plus 1, yeah. Okay. So then what? Well, this is then less than or equal to m, right, times 2 pi r divided by what? 2 pi. The I doesn't matter, right? And this is r to the... There's really a protest out in front? It's exciting. I want to go out and see it. I haven't really seen many protests in real life. It's exciting. Exciting. I feel like it's not going to be as exciting as I'm hoping, though. Like I've said before, you guys don't even complain about the projectors here, you know? So, I figure. You guys got to start with complaining about the stuff that surrounds you before you get to bigger things. I don't know. Let's see here. R to the n, yeah? So, doesn't look good. Doesn't look good for a sub n if we have what? If n is... Now remember here, n is an integer, right? So it could be positive or negative. So don't let appearances deceive you. If n is what? If n is less than or equal to minus 1, then 1 over r to the n is really equal to r to the minus n, which is r to a what? It's r to a positive power, right? And as r goes to 0, what happens to that? Yeah, this goes to 0 as r goes to 0. And certainly, we can shrink this circle to 0, right? So, therefore, a sub minus 1 equals a sub minus 2 equals a sub minus 3 equals dot, 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 equals 0. And what are we left with? What's that? Oh, okay. We have power series, right? So we're left with f of z is equal to a sum n equals 0 to infinity, right, of a sub n times z minus z naught to the n. Now, to be fussy, right? And I think this is something that books and myself are probably not as careful about as we should be. You know, once I write, if I'm thinking of f as being the Laurent expansion of f on the annulus, technically speaking, this could be thought of as an extension of f, right? So perhaps even at this stage, it would be more responsible for me to put like a tilde here or something, because the domain of that is the whole complex plane, right? Puncture plane? I don't know. Well, but anyway, this much I should say. You know, this f tilde, definitely we have f tilde of z is holomorphic where? It's holomorphic on the disk. You know, disk centered at z naught, right? Radius sigma, I suppose. I'm not sure I really need all this, but what was the definition of removable singularity? So my larger point is that we can just say, okay, so here's the deal. F of z, well, f tilde of z can be equal to, it can be equal to a sub naught for z equals to z naught, and it can be equal to f of z for, you know, 0 less than modulus of z minus z naught less than sigma, which shows you that, in fact, the singularity is removable. The definition of removable singularity was, we've already reached the definition of removable singularity before I wrote anything in red. Like, the proof is really done at that point. Once you've shown that the Laurent decomposition of the function centered at z naught contains only non-negative terms, by definition of removable singularity, that shows that z naught is a removable singularity. What I'm now explaining is the terminology removable singularity, which is that we can define a related function f tilde, which extends f to a holomorphic function on the whole disk simply by adjoining the obvious value that it should have at the center point, which is a sub 0, whatever that is, right? I mean, a sub 0 you can calculate by one of these integrals, right? A sub 0 would be the integral of f of z dz over z minus z naught to the first power over any circle you like in there. That will calculate what that is. Now, to give you a more simple example that we don't need to do any integration for, because we can just do a direct calculation of Laurent series, a good example would be f of z is sine z over z, right? This is 1 over z times z minus 1 over 3 factorial z cubed, right? And so, you know, this, you know, as it's given, is not defined technically for z equals to 0, right? But if you calculate the Laurent series expansion around 0 for this function, what do you get? It's the same thing you get by just canceling things here. You get 1 plus, you know, or rather minus 1/6 z squared plus da 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 da. This would be the a sub 0. And here my z naught is 0 in this example. Okay? Yeah. So that's the removable singularity. The next is the following. Theorem 11.2.6. All right, here we go. Excuse me. So let Z naught be isolated singularity. Isolated singularity of F. Then Z naught is a pole of F of order n if and only if F of Z is equal to G of Z divided by Z minus Z naught to the nth power, where G is holomorphic at Z naught and G of Z naught is not equal to 0. All right, so here we go. What's the forward direction of the proof? Essentially just the definition. By definition, if it's an isolated singularity, we're going to use the Laurent series expansion about Z naught. So the Laurent series about Z naught gives F of Z equal to the sum k equals minus n to infinity of a sub k Z minus Z naught to the power k. And it's not just the Laurent series, it's the Laurent series about Z naught gives since Z naught is a pole of order n. Right? By the definition of pole of order n, that means that the Laurent series has only finitely many negative terms in its expansion, and we can start at a leading non-zero negative term, which defines the order of the pole, which I've said is n here. All right. Then what you got to do is just kind of, really not much to this. What you have, I mean, we do know that a sub minus n is not equal to 0, right? That's what it means for it to be the pole of order n. So all you have to do is just kind of think about what this looks like. And I'll forego the summation notation for just a bit so everybody follows me better. Z minus Z naught to the n, yeah? Plus a sub minus n plus 1 over Z minus Z naught to the n minus 1, right? Dot, 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 dot. Eventually we get to a sub, what do we get here? Well, and so forth. I mean, eventually we get to things like a sub 0 and then a sub 1 times Z minus Z naught. I don't even know if I really need to write down what I just wrote down. Just my point is eventually you get to positive powers, okay? Fine. The larger point here is we could factor out 1 over Z minus Z naught to the n, all right? And if we do that, what's that leave us here? Is a minus n, right? And then plus a sub minus n plus 1, Z minus Z naught, dot, dot, dot. When I get over to here, I'd have like a sub 0 times Z minus Z naught to the n, right? And then a1 Z minus Z naught to the n plus 1, and so forth, right? And the point is, the thing I wrote in square brackets just now, right, is holomorphic, right, at Z naught. Because we know the series converges. I mean, it's the Laurent, you know, we already have the convergence of this Laurent series, and this is just part of it. So a subpart of a series that's convergent still converges, yeah. Anyway, this is exactly that G of Z I was talking about. And what's G of Z naught? it's a sub minus n, which is not equal to 0, right? And so that's the forward direction of this proof. And I'm not even going to write the reverse direction. The reverse direction is almost the same calculation. All right? And then, so in the reverse direction, right? I said I won't write anything. That's not entirely true. I'm just going to write a little bit. If I start with this, yeah? Then what would I do? I would expand. G is holomorphic, right? So it has a power series expansion. It's analytic. And then if you look at that, that gives you a Laurent series, right? So you have this Laurent series for F. And that must be the Laurent series, which means that that shows that it has a pole of order n. Because when you expand this out, you have the same format we did to start with. Okay, so that's the other direction of the proof. All right? Okay, so I have some kind of interesting calculations I should put on the board. So again, if it's n equals to 2, it's called a double pole. If it's n equals to 1, it's a simple pole, right? So at the moment, I've just shown you one characterization. If it's bounded, we have a what? A removable singularity. If it's a pole of order n, we have a pretty nice understanding of what the Laurent series looks like, right? Now, you guys, when I've looked at other books before in complex, some books will define a Laurent series to require the Laurent series to have a pole of finite order. Like some books would reject things with an essential singularity as even being a Laurent series. I wonder if that was a quirk of the book that I looked at. It's certainly not, and my notes don't do that, right? The Laurent series could have an essential singularity. It could have. But certainly the case that we have a pole of order n or a removable singularity is the nicest case, right? Certainly that much is true.
In order to deal with essential singularities, you have to introduce some projection between the natural numbers and the integers, right? Like, think about everything.
Yeah, I'm afeared to start picking at where we're not being rigorous in here. I think we're being pretty rigorous. I mean, relative to a calculus class, I think we're doing pretty well. Relative to a real analysis class, I don't think we're quite there yet. Okay, so this is what I just stated, this theorem 11.2.6. Here is an example that makes good on it. So e to the z over, oh, you got it? Sorry, I've gotten burnt so many times with that. It's now part of my, I can't stop myself. Anyway, e to the z, it's like, it's fine. You don't trust me. Why should that bother me as a student? Let's see here. All right, I'll stop. E to the z over z minus 1 to the fifth. So e to the z is analytic everywhere, right? So from this, so e to the z is the g of z, right? And z minus 1 is the z minus z naught to the fifth. All I got to do is look at that and go e to the 1 non-zero, right? So my g of z naught is non-zero. I'm dividing by z minus 1 to the fifth. Therefore, pole of order 5. What didn't I do? This theorem doesn't seem like anything. You're proving it. It's like, oh, this is dumb. Like, why are we even proving this? But then you apply it. And you realize it just gave you license to not find the Laurent decomposition of that. and you can still say it's a pole of order 5. Now, admittedly, finding the Laurent decomposition is not a big deal. All you got to do is take the z and replace it with z minus 1 plus 1, and then expand e to the z minus 1 as the power series, right? But we didn't have to do any of that, and I can already tell you what the pole in the order is. I can tell you that the order of 1, the order of 1 is an isolated singularity, and it's a pole of order 5. This one here is a little bit sneakier because we've got sine of z plus 2 to the 5th over, now this is a little bit ambiguous, but what I'm saying is there may be, I could afford a couple more parentheses here, right? Like this is sine of z plus 2 to the 5th. It's not sine of z plus 2 to the 5th. That would be something else. But might actually behave the same here as far as the pole is concerned. Yeah. All right, anyway, so this gives me that, and I got that. And then what do? You clear out things like you can. In other words, I will try to cancel out as much as I can, leaving a non-zero coefficient here. And that's my g. That's my 1 over z minus z naught. I can tell now it's a double pole, right? Does that make sense? Okay. Yes?
Can you not tell that from the original thing because it has the power 2 on the
But
bottom?
no, you can't, because this upstairs is competing against that. See that? In fact, I don't think this is right. This is bogus. It's totally bogus. What am I actually calculating here? It's not as advertised.
Just sine of.
Yeah, I'm looking at the sine of z plus 2 cubed divided by z plus 2 to the 5th, right? In fact, what's given, what's written here, has a removable singularity at minus 2. Because the numerator has a leading expansion to like 5th order, the denominator's leading expansion 2nd order, so it leaves you like a, in fact, it's got a 0. I'm not sure, it's not even well, no, it's removable. It's removable. It's just once you remove it, actually once you fill in the removable 0, you don't just have, you actually have a 0 of order 3, I think, for this expression. Yeah. You have the same issues with holes in the graph in like pre-calculus, right? If you take a parabola, right, and you have it bounce off the x-axis, and then you delete the little hole, delete the bouncing point, then if you were to fill in the hole there, then you'd have a 0 of order 2 in your graph in pre-calculus, just the same. This is not a complex thing. It's just when we fill in holes in graphs, we can get a lot of different behavior. This one happens to be a triple 0. Now, fixed it though. I need to edit my notes. This is the more interesting example. This one here, see the dominant term in the numerator is 3rd order and 5th order, so in net we get a net of 2 downstairs, which gives us a pole of order 2. Intuition is right. Like you can think about it intuitively, but I'm saying we don't have to use just intuition, we can use this theorem to be careful. Yeah? Okay. This is a terribly useful theorem. Z naught be an isolated singularity of f. Z naught is a pole of f of order n if and only if the reciprocal function is analytic at z naught with a 0 of order n. It's a wonderful theorem, right? The proof is right here. So if f has a pole of order n, that means we can expand f like that, right? So what happens if you flip it? Flip it. You've got z minus z naught to the n over g of z, right? So if you plug in z naught, you get 0, right? anyway, that is exactly a 0 of order n for the reciprocal function. That's the theorem. And vice versa. If we start with, well, did I just do a bidirectional proof here? Remember, probably can. It's essentially that, f having a pole of order n means that. 1 over f having a 0 of order n means that. But these don't have to be, in principle, those could be different functions, I guess, but what's that? Oh, conversely, I've got the conversely. Oh, I'm sorry. Conversely, this has a 0 of order n, then we have that. But then if you just rewrite this, this gives you f is equal to what? Good grief. This gives us f is equal to that. And then this, I can rewrite 1 over h, I can say is g. And because, remember, h of z is non-zero, h of z naught is non-zero because it's a pole of order, it's a 0 of order n, that means that g of z naught is defined, and the reciprocal of a holomorphic function is holomorphic provided that it's non-zero, as this one is. And there you go. We go back to the theorem 11.2.6 that shows that it's a pole of order n. Now, again, this doesn't seem like much when you first see it, but I tell you what, here's a powerful application right here. If we have 1 over sine z, this has a simple pole at n pi. Now, to do that directly, that would obligate you to calculate the Laurent expansion for the reciprocal of the sine function. Now, we could do that. It's within our power. But man, it's nice that we don't have to. All we have to do is go, hey, you know what? This is sine z, right? We can expand that as minus 1 to the n times z minus n times pi plus this stuff, right? And that makes it manifest that sine of z has a simple 0 at n pi. Now, we've done this a different way before, right? How else have we shown that sine of z has a simple 0 at n pi? We said, okay, first of all, f of n pi is 0. Second of all, f prime of z is cosine z. And cosine of n pi is minus 1 to the n, which is non-zero. Therefore, n pi is a simple 0 of sine, right? I'm showing it's a simple 0 by simply manifesting the power series expansion and identifying from this expansion that it's a simple 0 because it's got a leading first order term, yeah. This is a beautiful calculation. He does something really, really interesting in this calculation. I have a handout. I'll give it to you in a minute or two, okay? What he does in that calculation is he uses the existence of the Laurent decomposition to dodge a calculation. Essentially, well, I'll have to let you look at it. We can talk about it next time. Now, so here's another one. You can look at this expression. It's got a pole of order 3 at 0. It's got a pole of order 6 at 2 plus 3i. I can see that because you can identify the g of z in both cases and see that g of z naught is non-zero at the singular point. It's kind of silly, but there it is. Now a definition that's important and will be with us for the rest of the course. We say a function f is meromorphic on a domain D if it's analytic on D except possibly at isolated singularities where it has poles. So in other words, a meromorphic function is one which does not have an essential singularity at any of the singular points in its domain, right? And also it only has isolated singularities. You couldn't have something that has like a whole line of singularities somehow. This would not be a meromorphic function. You might wonder, how could you create a function that has a whole, circle of singularities or something like that? You might wonder. So an example of a meromorphic function would be an entire function is meromorphic on C because what's an entire function? It's holomorphic on C, right? So how many poles does an entire function have? Nada, right? That's the thing. Holomorphic functions don't have poles. But on the other hand, an entire function need not be analytic at infinity. right? For example, sine of z is not analytic at infinity. And so sine of z is not meromorphic on the extended complex plane, although it is meromorphic on the complex plane. It turns out rational functions are meromorphic on the extended complex plane. See, because the rational function can be written as, I mean, this is the thing we study in more depth going on, but essentially the point is that a rational function has what? P of z over q of z. What can you write? You can write that as like, you know, say f of z plus the remainder of z over q of z, right? So what happens as z goes to infinity, the polynomial piece blows up, right? But it's got finite order, right? So actually this amounts to having a pole of whatever order that is at infinity. And this piece just goes to 0 at infinity. Vice versa, if you're at any finite point, you have at most a pole from these kind of terms, because you're just dividing by a polynomial which has isolated zeros. And so that's why any finite pole of a rational function is going to be a pole. I mean, any finite singularity is going to be a pole for a rational function. And the polynomial piece just also gives us a pole at infinity. So on the extended complex plane, rational functions are meromorphic. This is the partial fractions decomposition, in fact. So here's the next result. If z is an isolated singularity of f, z naught is a pole of f of order n greater than or equal to 1, if and only if the modulus of f of z goes to infinity as z goes to z naught. So I'll start next class by proving this one. And past this, there's the result of the Casorati-Weierstrass result, which characterizes how essential singularities misbehave, right? So, but I don't think we should rush through this material. I think this is kind of important to understand carefully. So, I have like a minute left. So, I should tell you, there's a story. There's a famous story. There's a plane that was flying over the Alps, and it was transporting a Russian physicist and I think there was I think it was a Jewish pediatrician, and then there was a janitor from Poland. He was going to work. I forget where the plane was going. I guess it was probably going to maybe I think it was going to Siberia. That's what it was. And they were traveling over the Alps, and they had trouble. And the pilot had a heart attack, and so they what can we do? What can we do? And the Russian theoretical physicist says, I'm a theoretician. I can't fly the plane. I don't know what to do. The other guy says, well, I'm a pediatrician. What can I say? I just I fix little babies up. And then the janitor says, I'm just a simple pole in a complex plane. I don't know what to do. So there we go. You have now heard the joke, which only a certain fraction of the population can appreciate. There you go. So we'll be talking about simple poles and complex planes.